Good morning. This week in lab we have another lab activity looking at radioactive decay. And for the lab today, what we are given are 5 different radioactive samples of different isotopes. So these different isotopes are going to have different half-lives to them, which, they're going to be decaying at different rates. And what we want to be able to do is do a series of measurements just of the decay rates and use those to determine what the half-lives are. So actually be able to go in and take some different isotopes and find out what the half-lives are. Now, we have a data sheet, actually, so I do have the numbers. So these are the numbers that we have on the data sheet, and if you notice on the data sheet, the times that we're going to be looking at, we're going to take measurements at what we call t equals 0. We'll take a 1 minute measurement of the decays at this time, and then 10 minutes later, and then 20 minutes later. And then what you'll see from the data tables is that then shifts into hours. So at first we're taking a series of measurements every 10 minutes, and then that becomes a measurement every hour, and then later on it becomes, once a day we come in and measure them, and then we come in once every year, 10 years. So it looks like our final measurements are made either 10,000 or 100,000 years from now, depending on how you read the table. So, so today's lab is not going to be based on actual measurements that we've taken. So these are going to be a set of data that has been generated for these different 5 radioactive isotopes. And what we're going to do is put the pieces back together to figure out what the half-lives really are. Now, the disadvantage of today's lab is you'd say, well, it's not based on actual measurements. On the other hand, what this is enabling us to do is think in terms of a long-range series of measurements. So what if we did have something that, that had half-lives in the thousands or tens of thousands of years? It would be very interesting to be able to take that sample and actually follow it. Now, we do have samples of materials that we've looked at in class that we've learned about that have half-lives in the thousands or even millions or billions of years. And for those, by knowing the sample size that we have and then measuring their current rate of decay, we're able to calculate what the half-lives would be. We don't have to wait 1 billion years or 5 billion years to measure the half-life of uranium, for example. But we could, right? You could imagine doing this. And so that's what today's lab is kind of thinking in terms of. Now, we're expecting that the decay rates are going to drop off exponentially. These are the formulas that we've used to keep track of the decay rate as a function of time. And then right along with it, a very, very similar formula that tells us how many radioactive nuclei are in our sample as a function of time. And then there's a relationship between the lifetime, the decay rate, and the number currently in the sample. And then I also wrote down the formula for figuring out what the half-lives are. So we can work from these formulas. We can work from these data tables that we've got. Now, there's actually 5 different samples listed here. And if you look at the data tables, what you're going to find is that some of these are very short-lived isotopes. They may only be around for a few hours. Okay, so we've got to measure those very quickly and get a series of measurements made on all of those. Some of the other samples are going to be around for days or years. Some are going to be around for thousands of years. So of these 5 samples, the samples that we are working with, just to let you guys know, are, I'm going to say they're from elements that you've heard of. They're not kind of less commonly known elements. They are commonly known elements. They are common isotopes of commonly known elements that are in our 5 samples that we've got. So for each sample, I'm going to say you want to go in and generate your own data table for each sample. Now, there's one complete set of data that's been provided. The problem with that is because we started out by measuring every 10 minutes, and then we went to hours, and then we went to days, and then we went to hundreds or thousands of years, we need to get a consistent time scale going on. So I'm going to say, pick the time scale that applies or is relevant to the sample that you're looking at. If you're looking at something that looks like it's going to be gone within a few hours, then maybe you want to use minutes or hours as a time scale. If you've got something that seems like it's lasting for days, maybe use days. If you've got something that looks like it's lasting for years, use years as the time scale. So use whatever time scale seems appropriate. And then for each one of the samples, we want to generate a graph. Now, make sure that the data gets plotted here, as always. So there is the data. And then what we would like to do is an exponential fit. So there is a fit curve that we will make to the data. And from the fit curve, we're going to be able to go back. It's going to be a function that looks like this. And then from reading off that formula, we're going to be able to figure out what the lifetime is. Now, if you don't want to do the exponential fits, you could go back and do a logarithmic fit. So the other option, you don't have to do both of these, you have to do one or the other. The other option would be to do the logarithm as a function of time. And if we take this formula and we put it into a logarithm, what that would become is the ln of r is equal to the ln of r naught minus 1 over tau times the time. So that's what the formula would look like if we're going to plot it here. And that would mean for your data tables, you would need to go in and take the logarithm of each of those numbers, but that's doable, right? Once you've got a series of numbers entered into a spreadsheet, the next column over just becomes the logarithm of those numbers. So either go with the exponential fits, or if you decide, you can do the ln of r as a function of t. And for that, what you're going to find is that the data is dropping off linearly. So on this one, the tau would be 1 over the slope with a minus sign. So you would take the slope, take out the minus sign, take the absolute value of the slope, and then take its inverse, and that would give you the lifetime, the tau value. Now once you get tau, you can come up with the half-life. And once you get the half-life reliably measured, you can go to Appendix F in our textbook. So you can go to Appendix F and or another table online somewhere. But again, Appendix F has enough of the isotopes in there. All of these are going to show up in that list. But it's not such an extensive list that you get overwhelmed with all the isotopes. Because as you know from class, there are like thousands of radioactive isotopes out there. So anyway, we want to kind of focus in on the ones that are the more common ones. So once you get the half-life, run through those tables, look for what isotopes you think these are, and then you can also, from the fit, if you've got this fit with a function that's r naught, e to the minus t over tau, hey, take a look at the value of r naught from the fit, and that will give you r naught for the sample. What we want to know is what was the original decay rate, right? Now you might think, well, isn't the original decay rate that number right there when t was equal to 0? But remember, there's statistical fluctuations going on. And the r naught that we want to get is likely a better measurement than if we just take one data point. So it could be that that initial data point, there was a little bit of a fluctuation there. And so the data point we want will be better, a more reliable number if we take the one from the fit that we're using for that data. Now, once we get R naught, and we've got tau already that we've determined, we can figure out the sample size in terms of number of radioactive decay nuclei that we have in the sample. And then from there we can move on, and if we know the isotope, then we're gonna know what the molar mass is. So once you get the isotope, that's gonna allow you to get a molar mass. And so by knowing the molar mass, that's going to enable us to take the number of nuclei and convert that into a mass of the sample that we're given. So that's the list of values that we want to come up with for each one of the isotopes. And then we want to be able to identify all the isotopes. Okay, so what does the setup look like? If we go back to one of our tables and set this up, it looks like getting out the Geiger counter again. So we've looked at the Geiger counter before, and so go back and take a look at the Geiger counter if you want to, and see what that would look like. But in any case, this is what we're going to be completing, is determining all of these values from the decay rate data that we have been provided with. Let me phrase it that way. All right, so if there's any questions on this, let me know, stop by, and we can take a look and see what questions you guys have.